we're going to see Faraday's law. Here we have a current loop. So this is a loop and is carrying some current I. Could be, let's say, in this direction. Let's say we have a solenoid or something that we have, so this could be a second loop. If we put a conductor here, so a conductor produces a magnetic field, so we would have some magnetic field here. And we know from Ampere's law that a electric field or change in the electric field to the current produces a magnetic field. If we have the battery connected, here's some battery connected, we will not see any change in this current. If we have it disconnected, we also will not see any change in the current, but at the moment to connect it or at the moment of disconnect the battery, we could see a change in this current. We could see that maybe more current would be flowing. This is because the change in the electric field, change in current, could lead to a change in magnetic field. And Faraday observed that the change in the, not precisely the magnetic field, but change in the magnetic flux in dt, this produces a voltage called the electromotive force, that this is equal to the electromotive force. We define it as the circulation around for the electric field, or use d dot dl, well, the closed loop integral of E dot dl, or if you want the circulation, it is the circulation of E is the curl of the electric field. This is equal to the partial derivative of the magnetic flux with respect to T. So we have it in this is the differential form of Faraday law. The other way is just like this. The closed loop integral of E dot dl is equal to the change in magnetic flux with respect to time. You can convert this from this just by the analogy of the concept, but also from some theorems of multivariable calculus. We have the integral of a could be any vector, let's say the vector p, thus the normal vector the a. This is equal to, well, this is the integral, but because we have the a, you could also write it as a double integral because it's a surface integral. But this is equal to the integral or double integral of the curl of the vector, or the circulation of the vector. Now here, we know that the flux, magnetic flux, is equal to the closed loop integral of the magnetic field times the area vector, or you can write it as the normal vector to the surface dot dA. So here we have a vector. This is our vector, and so we can write this as the change in, or if we take the change in magnetic flux, we would have the change in this, but it is the derivative with respect to time. So anyway, we have that the change in the magnetic flux is equal to the electromotive force. We will see that we can produce a change in the magnetic flux if we change, it would be rare to change the magnetic field. Usually we could change either the area, or we could change the angle between the magnetic field and the normal vector, or the angle that makes with the surface, because here we are taking the dot product. So we need to multiply the magnitude of each one of these times the cosine. Actually here it is not just the flux or the change in flux, is the negative of the change in flux, because this current is producing some change in the magnetic field. The magnetic field will produce a change in the electric field that will generate a electromotive force, but this electromotive force is a current going in some direction around this closed loop. Now the current will go in the opposite direction as the first current, because this is called Lenz law. Lenz law. This is that the change in the magnetic flux produces a current that is opposing the first current, or is opposing the magnetic field to increase, because if it goes in the same direction, then this again would produce a change in the magnetic flux, and this magnetic flux produce again a change in the electric field. Again, the current will be in this direction, and so they will be like so to infinity. So in the intuitive way, is the change in the magnetic flux produces a electromotive force in which the current goes in the opposite direction to the initial current, or to the magnetic field. So this minus is just to remind Lenz law, that is the opposite direction. And so now in the next video we will see what would be the electromotive force, the power, the electromagnetic force, and many calculations when we apply Faraday's law. We will see it in one video when we change the area, and in another when we change the angle that the magnetic field does with the surface.